Hello everyone, welcome to my talk on mitigating slow instances in large-scale streaming pipelines. This presentation is for SIGMOD 20. Anyone interested can further refer to the paper in the conference proceedings. At Microsoft, we operate one of the largest data lakes, spanning thousands of machines. The data lake supports various batch, streaming, and interactive applications. Among these applications, the beam monetization pipeline is one of the most critical streaming workloads. It is directly related to the beam ads revenue and therefore must run 24/7 and satisfy strict SLO requirement. The pipeline is deployed to 3,500 containers. It is built based on a version of StreamScope and the Trail library. The library supports a temporal logical data model that can be embedded into many scale-out streaming frameworks. The StreamScope employs long-running processes to continuously analyze data. We use the Cosmos system as the external storage to distribute the data across different nodes. In this work, I will highlight some of the unique challenges when operating streaming systems at such large scale in the shared cloud environment. We will demonstrate how we reduce the tail latency of the pipeline with minimum additional resources. To clearly understand the problem, we show here a typical distribution of the job latencies of the pipeline. The median latency is about 12 minutes. Several factors contribute to the median latency. First, the pipeline contains multiple temporal operators over fixed or sliding windows. Examples include joins, merges, and aggregates. These windows are often in the order of minutes. Second, the pipeline generates terabytes of data which needs to be reliably transported between various stages. The overheads of storage, tracking, and reporting can add a few more minutes to the latency. On the other hand, the 99% tail latency of the pipeline is about 53 minutes, more than 4 times of the median latency. The reason behind this is mainly because resource contention in the shared cloud environment. As many batch jobs are also running in the same cluster, the contention for CPU and the memory can sometimes result in instances running slower than expected. Additionally, from time to time, the external storage system can be slow. This can add further delay to the job latency. The service level objective is defined on the latency at the tail. As we want to avoid SLO violation and provide a tighter SLO, we focus on how to reduce the tail latency in this work. To formally define the latency of the pipeline, we first introduce several terminologies. When a streaming pipeline is submitted for execution, the system compiler parses the script and generates a job graph. The pipeline consists of a set of stages, which in turn consists of a set of instances. Data records flow through adjacent stages in either an all-to-all or one-to-one communication pattern. Each data record is associated with a timestamp referred to as event time. The timestamp corresponds to when the data is generated. We use the watermark to represent a notion of input completeness. Specifically, the watermark WI indicates that instance I has processed all data with timestamp less than WI. In this example, instance 1 has finished processing all the data generated before 10 o'clock. We further use the watermark latency to represent the delay between the watermark and the current time. In this example, at time 10:05, instance 1 has a watermark latency of 5 minutes. As data records flow through the pipeline, different stages have different watermark latencies. We define the end-to-end latency of the pipeline as the watermark latency of the final stage. In this example, the end-to-end latency of the pipeline is 11 minutes. The 99 percentile latency required in the SLO is based on this end-to-end latency. As we mentioned, the tail latency of the pipeline is high due to various reasons such as resource contention and the issues related to underlying storage systems. From the perspective of the streaming system, these problems manifest as slow or idle instances. A slow instance has a watermark lower than its stage peers. In this example, instance 3 is 15 minutes behind its peers in the same stage. Moreover, a slow instance can impact all its downstream instances. In this example, all the instances after instance 3 cannot advance their watermarks beyond 955, as they are all waiting on the input from instance 3. In the paper, we present a detailed analysis of different slow instance patterns observed in production. These slow instances need to be mitigated in order for the pipeline to operate faster. The common approach to detect and mitigate slow instance is to compare the watermark latency of an instance within its stage. If the latency is higher than a stage median plus an epsilon, that instance is flagged slow. A new container is then requested and a duplicate of the slow instance is started. The duplicate starts from the last stable checkpoint and quickly catches up. Once the catch-up finishes, the system switches to the new duplicate and discards the original slow instance. Depending on the value of epsilon, we can classify a detection policy as either an aggressive policy or a conservative policy. For example, configuring epsilon to be 3 minutes gives us an aggressive policy. In general, aggressive policy should identify slow instances faster and leads to a lower latency. However, when we apply both the aggressive and conservative policy, the tail latency of the pipeline is similar. In certain cases, as shown in this figure, the aggressive policy even leads to a higher tail latency. To better understand this behavior, we examine the resource requests issued by both policies over time. It turns out that the aggressive policy requests almost an order of magnitude more containers than the conservative one. In a single policy cycle, the aggressive policy can request more than 250 containers, while the conservative policy never requests more than 30. Moreover, when the aggressive policy is applied, about 40% of these container requests are not granted. Combined with the fact that there are redundant container requests, some real slow instances are not mitigated. To improve the performance of either the aggressive or the conservative approach, we propose a two-step approach called Spur. We still believe that detecting slow instances early is necessary to keep the tail latency low. It is only that we should start duplicate in a smarter way. Spur aggressively detects slow instances and then applies smart filters to reduce the number of container requests. The filters consider 3 aspects of the pipeline. Due to the time limit, I will only talk about the first filter that removes dependent slow instances. The other 2 filters are detailed in the paper. The first thing coming to our mind is that not all slow instances are independent. In this example, both instance 6 and instance 9 are 10 minutes behind their stage medians. However, instance 9 is apparently slow due to its slow parent. On the other hand, there can be multiple independent slow instances at the same time. In the second example, both instance 3 and instance 6 are 10 minutes behind their stage peers. Given the outward communication pattern, the slow instance 3 should have the same impact on instance 4, 5, and 6. However, instance 6 is still 10 minutes behind instance 4 and 5. We can conclude that instance 6 is inherently slow. To determine which slow instance is dependent on others, we define the relative watermark latency. The relative watermark latency of an instance denotes how far its watermark is behind its parents. In the first example, the relative watermark latency of instance 9 is 1 minute, the same as all its stage peers. This indicates that instance 9 is not inherently slow. In the second example, the relative watermark latency of instance 6 is 10 minutes, distinctly higher than its peers. In this case, we should flag both instance 3 and instance 6 as slow and start 2 duplicate containers. We evaluate our approach at a very large scale and compare it with both the aggressive and conservative approach. We run the same pipeline at production scale. We measure the tail latency achieved by various mitigation approaches. For each approach, we also report the additional resource requested during the mitigation. We operate the pipeline both with and without the injected anomalies. A complete pattern of observed anomalies is presented in the paper. Our anomaly injection is highly configurable and covers more than 99% of the anomalies observed in production. I will use 2 examples to demonstrate the improvement of Spur. First, when we inject 20-minute anomalies. Both the aggressive and conservative approaches have similar P99 latency. However, the aggressive approach makes much more container requests. On the other hand, Spur leads to the best tail latency speed up while requiring similar resources to the conservative approach. In this example, Spur reduces tail latency by 38%. We observe similar improvement in other settings. For example, when we operate the pipeline without simulated anomalies, Spur still achieves a far better tail latency. A detailed report can be found in the paper. To conclude, we discussed how to mitigate slow instances in large-scale streaming pipelines. With careful design, a mixed approach of aggressive detection and smart filtering can help us tighten the service level objective with minimum additional resources. Thank you.